based on, this is work with a whole lot of people whose names I'm just listing here. I'm not going to read off all of those. All right. I'm contractually obligated to put the slide in because I'm from Hawkins. I have to have WMAP in my slides. This is our rough image of how we think the universe has evolved. If we look at the oldest light in the universe, the cosmic microwave background, and we put in some cosmological assumptions, we have to assume a cosmological model to be able to extract information from this. Specifically, if we assume lambda CDM, we can get lots of interesting parameters out of this, including how fast the universe is expanding today. It's the Hubble constant. And we get a value of something like 67.5 kilometers per second per megaparsec. But we can also figure out how fast the universe is expanding by looking at the late universe. For example, the Cepheid supernova distance ladder. This actually only takes in astrophysical assumptions, and we get something like 73.5-ish kilometers per second per megaparsec for the expansion rate of the universe. These two numbers are really close, but their errors are now really small, which leads to our beloved Hubble tension, which is now roughly at the 5.6 sigma level, which is pretty high by just about anyone's standards. But this is not the only interesting anomaly in cosmology. There is another one. Besides how fast the universe is expanding, besides a homogeneous isotropic effect, we can also notice that, well, the universe is not homogeneous and isotropic. It has lots of fluctuations. You have a galaxy here, you have a void here, you have another galaxy here. So we can think about what matter density fluctuations are doing, or what the amplitude of the matter power spectrum is doing. This parameter captures that amplitude, and we can again get an estimate of it from the CMB. We get one number. In the late universe, we can look at how galaxies are lensed by other masses in front of them. Any mass in front of a galaxy will slightly distort its shape. That's what weak lensing does. And we can get another measure of the same parameter from there, including some cosmological assumptions. These parameters, again, have a small tension between them. Not as big as the Hubble tension, but certainly at a level that's interesting to think about. So I'm going to be talking about both these tensions and how you might solve them if their solutions were new physics, how you can solve them with specifically early dark energy, what kind of challenges you face if you do try to solve one or the other tension, and how we can move forward from there and go towards some new concordance model of cosmology beyond lambda CDM. So let's start with the Hubble tension. If you want to change the Hubble parameter with new physics, you change it for the CMB, because the CMB is the one that has a model-dependent Hubble parameter. The CMB measures the Hubble parameter using this parameter, theta star. Now, if you look at this map, which is a snapshot of what the density and pressure waves were doing at the redshift of the CMB, if you look at this, you can kind of see, oh, most of the patch sizes have some preferred size, some angular size. Turns out that it absolutely does have a preferred angular size, and in fact, that is the angular size. That corresponds to the farthest distance that sound waves travel in the early universe. And because we're incredibly good at measuring angles in astronomy, this turns out to be a very, very precise measurement. It is, in fact, the most precisely measured parameter in all of cosmology. That angle corresponds to the actual physical size of the sound horizon, the farthest distance that sound waves travel in the early universe, and the distance from us to the CMB. So it's just geometry. It's just basic stuff here. Now, the denominator of that fraction, the distance between us and the CMB, depends on how the universe expanded since the CMB was emitted. So here I'm showing you energy densities versus redshift in a lambda CDM universe. And your distance between you and the CMB depends on an integral over the post-recombination universe. The numerator, on the other hand, how fast and how far sound waves traveled, depends on the pre-recombination universe, or an integral over this portion. So this is a really interesting parameter. It captures both the early and the late universe, and it's incredibly precisely measured. Because it's a measurement, you have to hold it fixed. Fixing that, if we know that we want to increase the Hubble parameter, it immediately tells us that we need to decrease the sound horizon. This is something that's actually echoed in several other data sets. It's not just me blabbering on about the CMB. If you look at what prediction different data sets have for the size of the sound horizon, you get almost exactly the same thing as the Hubble tension, but switched. So the CMB in the early universe predict a large sound horizon. The late universe predicts a much lower sound horizon. Exactly the opposite of the Hubble tension. So this tells us, one, we know we don't want to ruin the good fit of the CMB, which means we have to change the size of the sound horizon to change the Hubble parameter. Specifically, we need to add any new physics before the CMB is emitted, so we can do this. The second guidance that we have is any new physics has to vanish in the late universe. I've gone on and on about the CMB, but if you don't make new physics vanish, then you might create new tensions in the late universe. Besides the CMB, there's so much other stuff that we can observe. We can see how the CMB is gravitationally lensed. We see galaxies, their power spectra, how galaxies are weakly lensed, supernovae, so many different things. All of these are consistent with the lambda CDM universe at late times. If you add any new physics in the late universe, you run the risk of creating a new tension with these guys where there isn't currently a tension. For example, specifically the CMB and baryon acoustic oscillations both trace the exact same physics. They both trace the physics of the size of the sound horizon at two very different redshift scales. Not only are they both consistent with lambda CDM, they're also consistent with each other, which means we can measure at redshift of 1-ish and redshift of 1100, the same scale, they agree. If you add any new physics between them, new tension. The late universe is also very consistent with lambda CDM with regards to supernovae. Supernovae strongly constrain anything up, like down to roughly a redshift of 0.15. And if you try to add new physics under a redshift of 0.15, you're not actually solving the Hubble tension at all. To measure the Hubble parameter in the late universe, you need to use supernovae that are far enough away that their recession velocity is dominated by the Hubble flow, which means that the recession velocity should primarily be coming from the expansion of the universe and not because of any peculiar velocities. That happens at roughly this redshift. Any new physics under that doesn't solve any tension. All right, so knowing these things, we can now try to resolve the Hubble tension using early dark energy. So what we try to do is change the size of the sound horizon. Specifically, we want to reduce it. If sound waves travel a shorter distance, then automatically sound horizon becomes smaller. Maybe we can do this by making the universe recombine sooner. And if we want the universe to recombine sooner, we can try and make that happen by cooling it faster. For example, through expansion. So we want the early universe to expand slightly faster than lambda CDM before the CMB is emitted. What that does specifically is this. So if you have just some predicted CMB and you force the Hubble parameter to increase, you go into disagreement with data. You're essentially magnifying the CMB to an extent that is not going to be in agreement with data. What we're going to do is literally reduce the predicted patch size at the location of the CMB. So after that, if it's magnified, it doesn't matter. We're still going to be in agreement with data. Specifically, how we do this is by adding another component to the energy density of the universe, which looks like this. Again, I'm showing you energy densities and fractional contribution over redshift. This new component looks like a cosmological constant at early times, and then at some redshift, it begins to rapidly vanish. It has to vanish at least as fast as the radiation. This is purely phenomenological right now. The parameters of such a model are how much early dark energy there is, so what is the amplitude of that curve, when it's injected, so the location of that peak, and how fast it disappears, or the slope of the left side of this peak. This phenomenology is, now we're achieving both of these. We're injecting new physics before the CMB and reducing the size of the sound horizon because we'll make the universe expand and cool faster. And it's disappearing in the late universe. So we are now consistent with the two requirements we set out for ourselves. Everything I've shown you so far was phenomenological, but it can be formed by numerous different fundamental models, including all of these ones that I have worked on, And all of these ones that I have not worked on, that other people have suggested for the same kind of phenomenology that we first proposed with early dark energy. I'll talk a little bit about each of these. Let me start by the first one that we started to think about. This is an early dark energy, which is very glitchy, and I'm sorry about that. These two plots are time matched. I'm sorry that they're not very smooth right now, but you can read them off together. So that is a scalar oscillating in a potential of this form. And that is what its energy density looks like, and its fractional contribution to the energy budget. And you can see that, again, there is some injection and then it disappears in the late universe. I know that that potential has its issues, but we'll get to that in a few minutes. All right. When we then throw such a model at data, this is what we get. Again, there's a lot going on here, but I will specifically direct your attention to this plot of H0 versus omega CDM. You can see what the lambda CDM contour is doing here in orange, and the local Hubble measurement bands. And you can see the Hubble tension between them because they're not overlapping. What early dark energy does is it both increases the error on H0, which you can kind of see here, where this the error budget on that 1D plot has increased, but it also shifts the H0 peak value to higher, to faster. Both of those effects together then resolve the Hubble tension, because you can see that these plots intersect at the 1 sigma level. They also improve the fit to data. We find that early dark energy fits data better than lambda CDM does. It fits just CMB data also better than lambda CDM does, which is really great. Moreover, we can probably detect it in the CMB. In fact, we have probably already seen hints of it in both ACT and SVD data. So I've painted a really great picture for you. We have the Hubble tension, but we know how to resolve it. Our resolution can be found by many different fundamental models. It can be detected in data, and it fits current data really well. But so far, I've concentrated on just one tension. There are actually two tensions in cosmology. So let's talk a little bit also about the sigma 8 tension. In terms of posterior contours, it looks something like this. Sigma 8 is the amplitude of the matter power spectrum at a certain scale, close to the nonlinear scale, but still within the linear regime. S8 is a parameter that was constructed to capture the most constraining direction of weak lensing surveys. So this parameter doesn't really mean anything physically. It's just the best constrained direction for a specific kind of experiment. That is the CMB expectation from Planck 2018. And then these two contours, the red and blue ones, the ones I'll direct your eyes to, those two are from weak lensing surveys, which mildly or not so mildly disagree with the Planck CMB. So I've told you already about one resolution we have to one tension. Why don't we just throw early dark energy at this also and see what happens? It doesn't help, unfortunately. So here I'm showing you the Hubble parameter and this new parameter we've been talking about, S8, and their local measurement bands. This is what Planck lambda CDM does in the filled-in contour. The unfilled contour is what early dark energy does in this regime. So early dark energy moves up in terms of Hubble, but it doesn't really move left as we would like it to. In fact, going from the lambda CDM best fit, which is this circle, early dark energy shifts its best fit to this cross. So it actually slightly goes in the wrong direction. So we have many positives of early dark energy, but we also have some hurdles. It resolves one tension, but it slightly worsens the other tension. Although it can arise from several different theoretical scenarios, most of these are still constrained to be injected around matter radiation quality. So we're creating a new coincidence problem, just like late time dark energy. Why does it show up right now? Why does early dark energy show up when it does? There's one particular formalism that does work really well, but it's a very contrived potential that has fine-tuning issues. Finally, although we're improving the fit to cosmological data sets, we need to include the local Hubble measurement as an additional likelihood to get this result.
So you might, for a second. you might be talking about this gets back to the thing you talked about lunch. So on top of the standard 6 cosmological parameters, there's parameters in this potential here that are in there that I don't see that are obtained from
Yes.
that are next. And how many parameters is this?
Yeah, usually it's 3 parameters, and it's these 3.
Okay.
So how much, when, and how fast it goes away.
Okay. And then that's better.
So most early dark energy models add 3 additional parameters to their fits. So it's lambda CDM 6 plus 3 early dark energy, so 9 cosmological parameters total, plus all your nuisance parameters and things. Yeah.
So, the way your dark energy distribution is because you are marking up the expansion rate prior to the CFD.
Yes.
And SA is kind of other story. Like sound horizon is not discoded.
Good question. So for the CMB specifically, H0 depends on the sound horizon. S8 does not. So you don't actually need to do anything at the background level to mess with the S8 tension. You absolutely have to do something at the background level to help the Hubble tension. And that also goes back to the fact that the Hubble parameter is about the isotropic homogeneous expansion of the universe, which means background level change. But the S8 tension is about the perturbative universe. How did matter density fluctuations evolve? So you don't need to do something at the background level. If you just change perturbations, you can probably fix that.
So suppose one tinkers with the matrix. So can you address both of them? Like suppose I modify the matrix.
Oh, you mean not do GR, but
yeah, just I modify the matrix.
time
dependent modification, and I do it in the post CFD.
Yeah.
And I address both because I can matter perturbation.
So for you will have to do 2 changes to the metric then. So one would be people have looked at allowing G Newton to change with a step function for the Hubble tension. So your step function then happens in the early universe, and then in the late universe, it's just one constant.
Yeah.
You would have to have another second change to G Newton in the late universe to change like late universe dynamics.
Yeah, but the perturbation can jump up.
Yeah. Yeah. You can do something like that. Sure.
So that one can address both. Let's say.
Yes. Yeah. Technically, G Newton is still a background change because the background equations depend on G Newton. So this still stands because there is a G Newton in there. Yeah. Okay. All right, so we have both positives and drawbacks of early dark energy. So what can we do from here?
Also one.
Yes.
So there is also 21 centimeter data. By any chance, dark energy your solution is in the right direction?
Oh, for edges, you mean?
Yeah.
Okay. Okay. I don't know how to put this. Yes and no. Let me see if I can. All right. So the early dark energies that I've been thinking about the most happen in the very early universe.
Yeah.
Really, the peak happens even slightly earlier. It happens closer to here at matter radiation equality. That does not impact 21 centimeter. It will not have anything to do with edges. If you have a second such field, so the same thing, same line, but I put it much lower. I put it at redshift of 10-ish. So I put it somewhere here. This peak is then shifted down here. Then you go in the correct direction for edges.
But that would solve your problem.
That does not solve the Hubble tension. In fact, it will make the Hubble tension worse. Yes, because you have to disappear in the late universe. If you add any any energy density to this portion of the universe, then you worsen the Hubble tension. Yeah. All right. So we have these obstacles for early dark energy solutions to H0. So where do we go from here? How can we now figure out what a new concordance model might look like? Let me start by talking about the last point, because I think most of you were here for the discussion right before this, which was how do we how do we deal with the fact that we have to include H0 when we're trying to fit early dark energy? Without using the H0 likelihood, we don't get the early dark energy solution. It turns out this is exactly because of the prior volume projection effects that I was talking about. I'm going to go through this really fast because I'm assuming most of you were here. Between the two statistical frameworks, Bayesian inference does have prior dependence, profile likelihoods do not. Profile likelihoods are the dashed curves here. For lambda CDM, you see that they pretty much overlap. There's no prior volume projection issues. For EDE, they don't. You get very different constraints when you use profile likelihoods for EDE. Then it becomes a question of whether we trust our EDE priors, because EDE is such an exploratory model. There's no reason for us to pigeonhole ourselves into certain priors and trust that these are exactly the right priors. Our priors can be differently behaved. There's no reason for us to have even flat uniform priors. Once you remove those assumptions, this no longer makes sense as a technique to use for statistical inference. That makes more sense. I put out a code that now does this. It's a publicly available code that calculates profile likelihoods very quickly and efficiently in cosmology. It's based on a simulated annealing optimizer. I can talk about that if anyone's interested, but I will just say, try properly. That's the code if you care about this stuff. This is the kind of output that you can get from it. This is the purple solid curve is a profile that's generated by my code. A blue curve is a profile that is generated by a non-stochastic algorithm, does not perform as well. And then the green curve is if you literally just take your MCMC, bin it, and in these narrow bins, ask what is my best likelihood point. You can see that an MCMC is not actually a great optimizer. It's not made for that purpose. It fulfills its purpose really well, but it's not a great optimizer. There's a difference almost of a delta chi-squared minimum of about 5 between the green and the purple curve. So if you want to do profiles, use simulated annealing and use my code. So profiles can give you really useful insight into models where you don't necessarily trust your priors, or you don't want your priors to bias your results. So we've solved potentially one of these issues, but what about the others? Now, for the others, we can still use early dark energy as a jumping off point. We already know we have a resolution to one tension from it. Maybe we can expand the early dark energy model to resolve the other things. And we can slightly change the model to deal with these fine-tuning effects as well. Finally, for this point, this new coincidence problem that early dark energy creates, we should actually use that as model building insight. It tells us that there is an interesting time in cosmology at which early dark energy appears. We should use that to try to figure out, can we postulate a model that talks to matter radiation equality somehow and uses that to trigger early dark energy? So that's one of the things that we thought about with coupling early dark energy to dark matter via chameleon interaction. So you have dark matter's energy density then gets modulated like this, and the scalar field now moves in an effective potential that looks like this, which gets contributions from both. And I'm sorry that this is, again, very jittery. For specific choices of the potential and for the coupling constant, you get a scalar that rolls in this sort of effective potential. Because this modifies the dark matter mass, it'll also modify the dark matter perturbative evolution. So it might have implications for the weak lensing SA tension, which talks about how matter density fluctuations have evolved. And then 2, this also ties the redshift of the appearance of early dark energy to matter radiation quality through this coupling. Let's see. Okay, another thing we've been thinking about is making early dark energy talk to late dark energy. You can do this by having a slightly more complicated potential where one part of the potential forms early dark energy. The second part of the potential then takes over in late times and forms late time dark energy. Its energy density, equation of state, and impact to Hubble all across redshift then look like these plots. We'll primarily concentrate on this one. There is an early dark energy like saddle point in the radiation eras, which means that there's equation of state of roughly -1 deep in the radiation era. Then early dark energy kicks in, and rapidly begins to dilute, which is this portion here. Eventually, it settles into a matter-like saddle point, which is there. And then finally goes to the dark energy attractor down here. So it starts at -1 and goes to -1. This was a really interesting model to think about because now we could tie two different eras of accelerated cosmic expansion to each other. But we found that specifically this model contributed too strongly during matter domination. It contributed too strongly to the late time universe, where I said we don't want to touch it, we don't want to add new things. When early dark energy pops into the early universe, it creates an early integrated Sachs-Rhodes effect. It makes your gravitational potentials decay, which boosts power in the cosmic microwave background. This is not making too much sense to you, it's fine, it doesn't matter too much, but essentially, the presence of early dark energy at early times requires an increase in your dark matter density. But if you have early dark energy also contribute to the late universe, this is going to require a decrease in your dark matter density. You cannot satisfy both at the same time, so this model doesn't wind up working very well and doesn't provide a good fit to data. All right, one of the last things we thought about was trying to get early dark energy to talk to dark radiation. I just made it talk to the entire dark sector, just like, give me something and I'll make early dark energy talk to it. Okay, so you have an uncoupled scalar field whose equation of motion looks like that. And if you have uncoupled dark radiation, its energy density just decreases as redshift to the 4th. That's why the -4 is there. Okay, if you couple these two, specifically via a dissipative process, you're then extracting energy density from this scalar field and dumping it into a dark radiation thermal bath like this. So it's a dissipative process that is tied to something like a friction to the scalar field. Doing this, you can still produce the same kind of early dark energy dynamics of using the combined system of the dark radiation and the early dark energy. So now we have early dark energy at early times, this blue curve, a scalar field, which dumps its energy density into this yellow thing, which is the dark radiation. Combined, this green curve then gives you the usual stuff we've been talking about, something that appears and then disappears. Its parameters are still the same. Amount of early dark energy, when it appears and how fast it disappears is now just a final equation of state of 1/3, which is just the usual one for radiation. The really fun thing about this model is that it's completely robust to the choice of potential. You can put in anything here and it's not going to change the dynamics because the potential of the scalar field never dictates the dynamics. The entire energy density from this is immediately dumped into the dark radiation. So V5 just doesn't matter. So we've solved the problem entirely of a bad potential for the early dark energy. We looked at this as a solution to both the Hubble and the large-scale structure tension, which is why I'm including these two data sets, a local H0 measurement and the dark energy survey constraint on S8. We found that it improves the Hubble tension, it doesn't really improve the S8 tension, and instead of early dark energy, the universe prefers extra radiation that looks like this, that's just ever present. This is slightly different from ineffective. It doesn't have the same perturbations as neutrinos or like massless radiation, because this radiation is strongly self-interacting, so its perturbations look different, which is why we actually do slightly better than massless neutrinos. But we still roughly suffer the same sort of constraints as adding massless neutrinos. But this model got us thinking about, well, what if instead of making early dark energy talk to dark radiation, what if we got late dark energy to talk to dark radiation? So now we're doing the same thing. We have this scalar field coupled to dark radiation via thermal friction. The interaction term in the Lagrangian looks like that. But we're now producing dark radiation in the late universe instead of the early universe. This was really interesting. So we set just some linear potential for the scalar field. We looked at a friction that depends on the dark radiation energy density, one that is constant, and we also compared it to quintessence. And the really cool thing was that 3% dark radiation is allowed by current data in today's universe. For reference, this is orders of magnitude greater than neutrinos or even photons. So hotter dark radiation and much more density is allowed by current data. And in fact, current data has the same constraints for all three of these. The kinetic component of dark energy is what current data is constraining. It doesn't matter what that kinetic component is going into. It can go into dark radiation, that's fine. Future data that is based on lambda CDM. I literally use lambda CDM to generate fiducial future data for the Simons Observatory and Roman supernovae, and I'm still allowing 1% dark radiation at 2 sigma. That is still a few orders of magnitude greater than photons. What that looks like is this, again, in terms of energy densities versus redshift. So you have matter, you have radiation, you have dark energy, and then this sort of dark radiation is growing in the late universe because you're generating. If you can generate it in the late universe, you completely skirt any early universe bounds. They just don't matter. And you also cannot distinguish them from quintessence at all with current data, or even with future data. So then we started thinking about, well, if we can't see the difference between this dark radiation and just dark energy with cosmological data, what if we looked at it in particle experiments? So then we started thinking about what kind of dark radiation bath particles can we have. So we still have axions in our radiation bath, which is just the scalar. We have the gauge bosons, which form the main interaction term in Lagrangian. And then we have either just dark photons or fermions and dark photons.
Actually, sorry, can I just ask a technical question? So like, when you say quintessence, you basically mean that first equation up there without the what? This equation. Yeah, you just mean, actually, no, go back. There was the scalar code equation you had.
Okay.
Yeah. Yeah. So you basically mean that's 43 letter sentence. Yeah. Upsilon.
Yeah.
That you basically mean quintessence that phi just evolving by itself.
Exactly. Yes.
And you say you can't tell it apart from quintessence just because. So and then you're just calculating that you're just doing the standard quintessence thing with that field, right? And you say you can't tell apart from this at the moment.
Yes, you can't. So the only thing that you can see is how much of a kinetic component there is to dark radiation, or dark energy. Whether that's in dark radiation or whether that's in the kinetic energy of a scalar field, data cannot tell it apart right now.
So the Z value when you start doing this can be 20 or something.
That's a really good question. To some extent, it is. So we were only interested in specifically generating it much later. You can stretch it up here.
But galaxy formations and those things.
At 3%, I'm not sure. But the truth is that we would have to do an n-body simulation with this to make sure. Yeah.
Because then you can go back to it. That would be also part of the story.
Yeah. Yeah, that's sort of the idea. Like, this is the exact same thing as
Right. You're just
yeah, it's the same thing as this.
lady.
Yeah. Okay. All right. So then we started thinking about what kind of particle experiments we might see. One specific experiment that would be interesting is one that detects dark photons. So we added interactions either through a fermion or directly with the axion to a dark photon, and then you allow this dark photon to kinetically mix with the standard model, which essentially just means one way or the other, we are able to convert some of the dark radiation in our dark energy radiation stuff into standard model photons down the line. There are already good constraints on these sorts of dark photons from FIRS, which I never remember the full form of. It is the Far Infrared Absolute Spectrometer. But this is what was on attached to the Kobe CMB experiment. So these are really old constraints that we haven't repeated. But this is coming from the black body spectrum of the CMB. Both of these constraints are. Resonant scattering is just coming from the photon plasma mass will give you a resonant scattering. So you get a slightly better constraint right here. There are many other constraints that you can get from the CMB primary, so the CMB temperature power spectrum, stellar cooling. So if you allow dark photons to take away some energy density from stars, then you would expect stars to cool faster. And laboratory experiments, things like light shining through a wall. So you get a really dark chamber and you try to look for any photons that happen to appear in this really dark chamber, a dark cavity, which would imply that a dark photon has crossed the wall and reconverted into a standard model photon inside the wall.
This part is kind of a, you want to make it visible, like you don't need this. There is no, you don't need any connection to the photon or any cosmology.
No, you don't. You absolutely don't. This is just to test whether if we had dark radiation, which cosmology allows at 3%, can we see it anywhere? So these sorts of dark energy radiation models written by my collaborator, Kim Berghaus, actually inspired this experiment, which is our best bet of being able to see this. It's called the Late Dark Energy Radiation Experiment, LEDERA. It's at JPL. And that has some limits on this cross-section of kinetically mixing with with standard model photons for certain masses of our dark photons, which is really cool. All right, so I've spoken to you quite at length about two tensions. We're still not fully sure whether these tensions are real, and it's still useful to ask whether they're real, but it's also interesting to think about what kind of physics would they suggest if they are real. I've hopefully convinced you that the Hubble tension requires an early universe change in order to resolve it. This change can look like early dark energy, and several different fundamental models can form this early dark energy. It improves the fit to data, and it can be detected by current and upcoming CMB experiments both. There are many challenges to early dark energy. For example, the large-scale structure, the S8 tension, the new coincidence problem of why early dark energy appears in matter radiation equality, and also thoughts about trying to improve the fundamental model of early dark energy. All of those can be addressed by improving EDE model building, which is what we tried to do by getting it to interact with several parts of the dark sector. Another challenge to early dark energy is prior volume effects, which we're trying to address instead with changing how we approach parameter constraints statistically through profile likelihoods, like properly. These models that we write down for early dark energy are interesting also because they're applicable to other eras of cosmic acceleration, including late dark energy, like I spoke about, and inflation, which my colleague has done extensive work about, and I will direct you to her papers. This sort of one of these models I spoke about, dark energy radiation, is really interesting because it allows for so much more dark radiation in the universe today than we originally thought could exist. Finally, we keep trying to smush these two tensions together. It's really elegant to be able to find one solution for both tensions. But these tensions inherently are very different. They might require two different solutions for the two different tensions, and we should allow for that. But finally, I've spoken to you quite at length about doing interesting things with the dark sector and how cosmological anomalies can give you insight into the dark sector. So I'll just leave you with, we should be creative about the dark sector when we think about new models.
That we're reading.
All right, that's all I have.
Okay, so question for, so basically, if I have a source for dark radiation, is that if I turn that source on, like suppose I have a source, I don't need it to couple to your quantum field.
Yeah.
I just have a source for dark radiation, then I solve this.
Yeah, you can have any source for dark radiation.
Then I can
Solve the Hubble tension.
like a late time of suppose
You can't solve the Hubble tension with like any late time things, really.
like even suppose injecting some dark radiation.
No, anything you inject into the late universe will definitely worsen the Hubble tension. If you try to take energy density away from the late universe, you might help it. But if you do that, then you will spoil the fit between BAO and CMB. So there'll be a new tension where right now they agree. Yeah.
Try to see the parameters. So basically, what you need a dark energy phi, which would come to the dark radiation, and then phi giving rise to this. So that's basically.
Yeah, so for the late time dark radiation, yes. So here we're just curious about how much dark radiation we
Yeah.
can have. If you have something that is not phi, if you don't touch dark energy, but you have any other field that creates this, then the maximum energy density in dark radiation will be it'll be limited by what your total energy density in this field is. You can never go above this. Yeah, so if you have a spectator field, which is like 1% of the universe, then the maximum dark radiation you'll be able to produce is 1%, which is, yeah, that's fine.
But that won't solve the,
That will not solve the Hubble tension.
that would just explain the constraint.
Yeah, exactly. It will just give you a dynamical framework for dark energy to be what it is.
A prime mass scale.
Sorry?
Can you go back to the A prime mass scale?
Oh, yeah.
Is that capped with a coupling two photons?
Yes.
So have you looked at, if you get to really like things, well, you could do it anywhere, but you could super radiate these particles. Because there are bounds, forget about any coupling, there are already bounds on like 10⁻8. MeV, 10⁻11 EV particles. LIGO has bounds on those already. You don't
Okay.
need any standard model couplings to super radiate, just need gravitational couplings.
I see.
So
Okay. Okay.
any
Yeah, we
photon-
should.
Yeah, so once you get to 10⁻11 EV and below, then they're astrophysically spinning black holes that can actually test some of these things.
Okay.
So supermassive black holes can get to ultralight.
I see. And this is the same sort of super radiance constraints that we have on photons.
No, this is,
A prime.
yeah,
That's
it's not
A
any
prime.
the existence of any photon.
Okay.
All you have to do is match the mass, which gives you a constant wavelength to the, essentially the light crossing radius of your black hole. So by seeing them spin, which we have spin measurements at different masses, seeing the existence of spin, you know you've not spun them down from super radiance, so you cannot have something that.
Okay,
exists there.
yeah, that's
I can show you
interesting.
the plots.
Yeah. We should add those bounds. Okay, that's interesting. Thank
Because
you.
it doesn't matter what your standard model couplings are.
Okay.
They
Yeah.
just zero.
All right. Thank you.
But the A prime mass does not have any bearing to your solution.
No, again, like all of this was just for like late.
Just that
Yeah, it was just for dark energy. Yeah, it was,
scale is, mass scale.
yes.
Any other questions? What's the layer, like, what specifically is it? What are this layer experiments?
Yeah, how do you mean?
What is it like?
Oh,
It's a JDR.
It's another similar thing where they have essentially a cavity and they're trying to detect photons that are converting.
Oh, okay. It's a
dark
terrestrial
photons-
experiment.
Sorry?
It's a terrestrial experiment, not space.
Oh, yeah. I think it's like they've already got a prototype, I think at JDR, yeah.
Perfect.
Either that or Caltech, I forget which one of them is doing. It's somewhere in Boston.
Questions, further questions? Okay, if not, let's thank. So if you're interested, the heading, the dealing with the, so, just email the link for. Okay, thank you.